Okay, let's move to rectification. So for this rectification also we use this general purpose, so rectifier type of diode. So last couple of sessions we discussed about the modeling of this diode. So we basically found two commonly used models for diodes. So one is called the ideal model. So the first one is this ideal model. So the other would be like simplified. So if it is an ideal diode, so we found that so the diode drop or the voltage across the diode should be greater than or equals to 0 to make it forward bias. And if the diode drop is less than 0, so we claim that diode is basically in reverse bias region. So if this ideal diode is forward bias, we can replace this diode with a kind of a short circuit element. So if the diode is basically in reverse bias region, we can replace the diode with a kind of open circuit element. So this is the modeling part of this ideal diode. So these are the two conditions that particular diode should be satisfied if it is in reverse bias or forward bias region. So based on the region that diode is basically operating, so we can either replace the diode with a short circuit element or a kind of a open circuit element. So if it is a simplified diode, so we basically consider this mean voltage or the barrier voltage also into account, and we found that if the voltage drop across the diode is greater than or equals Vk, we claim that the diode should be in forward bias region. So if it is the other way, so diode is basically in reverse bias region. So if this diode is forward bias, we can simply replace the diode with a kind of a DC source of value Vk. So if the dart is simply aligning with simplified model, if it is forward bias, then we can replace the dart with a fixed DC source of Vk. Fixed DC source of Vk. Vk volt. So this Vk is the knee or barrier voltage. Okay. So then if it is reverse bias as the usual manner, so we can simply replace this star with a kind of a open circuit element. Okay, so then we move to this rectifier, rectification. So we have two methods. One is this half rectification, half wave rectification. So the other one is actually full wave rectification. So this very first one is already discussed, half wave rectification. So it's very simple. We have kind of a rectified diode. We have resistor here, so this is the load resistance, and we basically apply input, which is a kind of a sinusoid. Vm sine omega t. Okay, so we have a diode here and a load resistor. So we basically feed a kind of a alternative type current, which we can model as Vm sine omega t. So Vm is the peak voltage and the shape of the alternating voltage is sine omega t. So we take the output across this load resistance RL. So this is your output. So this is your output and this is your input. So I stick to the sign convention like here, so which is basically demonstrating this figure. So I consider these terminals as positive polarities, this has the negative polarity or the potentials. So for the simplicity, we'll stick into this ideal diodes. So we'll assume that these are kind of ideal diodes. So what would be the output for these particular scenarios? So for the positive cycle, so if we consider this part, positive cycle, so then the input is something like that. This is the input now. So this is the voltage drop across the diode. So then we can claim that, so the actual voltage across the diode Vd should equals to Vi. So Vi during this positive cycle, this is basically greater than or equal to 0. If we basically refer these 2 points during this positive cycle, so we have 0 voltage at input. So otherwise the voltage appear across the input is basically greater than 0. So then in general, the voltage in the input voltage is basically greater than or equal 0 during its positive cycle, and is simply forward bias. So if the diode is forward bias, we can simply replace the diode with a short circuit element. So then we can replace this whatever the diode with a short circuit element. So then, so the circuit would be something like that. So we have this kind of input. So this is your output. So then from this we can simply say that the output is equals to input. So then during this positive cycle, the output is basically following. So next we move to the negative cycle. So then the applied voltage is something like that. Vh minus is plus Vi. So then the voltage drop once you apply Kirchhoff voltage law. So we can easily found that this voltage drop across the diode is minus of Vi. So this is less than 0 and that should be reverse bias. So if the diode is reverse bias, we can simply replace the diode with a kind of open circuit element, and then this circuit is basically simplified to this. So we have this input, so we have the output across this load, and due to this reverse bias operation of this diode, so we create a kind of a open circuit at this across this diode. So then the output and input is simply isolated from each other, and the out should be simply 0. So then this is the, so this is the out. So from this we can see, like, if we basically apply a kind of a sinusoidal signal, so we can get the output as the half wave rectified version. So it basically filter the positive cycles of this entire sinusoidal signal and clip this negative cycle off. So it basically pass this block and remove this one. So that's why we call it as kind of a half wave. So this entire wave is not rectified, so it basically remove the negative cycle and filter the positive cycle out. So then it means, like, if you have this kind of a sinusoidal signal, so you will basically have this half and this half only. So these are basically removed out from the output. So you have this kind of signal. So we have ultimately have this kind of signal. So this is the half wave rectification. So let's think about what about the value of peak inverse voltage. So peak inverse voltage is the maximum voltage Vmax, so that particular diode can manage during reverse bias operation. Okay, so the peak inverse voltage is actually the maximum voltage which this particular diode can manage during reverse bias operation. Keep in mind, this is very important, reverse bias maximum. So for this particular circuit, what's the maximum voltage appear across this diode when it get reverse bias? So by looking at this one, so we can claim that during this negative cycle, so diode get reverse bias. Okay, so diode get reverse bias. So then, so this is the voltage appear across the diode during that period T. So what is the open circuit voltage across this diode when it is reverse bias? So this is the reverse bias scenario. So this diode is basically act as a kind of open circuit element. So there won't be any current, so that's why we replace it with open circuit element. So then what about this open circuit voltage during this reverse bias region? So the reverse bias region, the voltage across this diode open circuit voltage is exactly equals to input. Okay, so then input is actually vary according to this formula, Vm sine omega t. Okay, Vm sine omega t. Yes. So then what is the maximum voltage appear at the input? So this V max is actually equals to Vm. So this is the maximum voltage, peak voltage. So then from this one we can claim that, so this is the input, actually Vi is actually Vm sine omega t, and during reverse bias operation voltage drop across the diode is equals to Vi, which is equals to Vm sine omega t, and V max is actually Vm during this reverse bias operation. So the input is directly applied across this diode terminal, and the open circuit voltage is actually equals to Vi input voltage. So Vi is basically behave as a sinusoidal signal, which we can mathematically model as Vm sine omega t. So the maximum of this input is basically Vm. So the max of input is basically Vm. So then, so the voltage drop across the max voltage across diode during reverse bias is Vm. So during this peak of the negative cycle, we basically apply the maximum voltage, which is equals to Vm. So otherwise, during, if this is the negative cycle, this is your Vm. So if during these places, so the voltage is less than Vm. So then basically we can claim that the peak inverse voltage of this particular diode should be at least Vm. So ideally it should be greater than Vm. Because let's think, if we select a diode with a peak inverse voltage less than Vm, what happens? So if we think about the characteristics, so this is the characteristic during this. So this is the peak inverse voltage. So this is your Vm. So then we know that during this negative cycle, we basically apply a maximum voltage of Vm. So but this particular diode can handle only a voltage which is less than this Vm. So then if this is the scenario, diode get burns, because this particular diode cannot manage a voltage of Vm. So let's assume your peak inverse voltage is somewhere around here. So once we apply this negative cycle, so if the voltage is beyond this limit, so then definitely that it cuts. So to avoid these scenarios, you should at least set a voltage slightly higher than this Vm for the peak inverse voltage. So then if you want to select a rectifier diode, so keep in mind, so Vm is the actually the peak voltage of the input. So this is peak voltage of the input. So let's assume you are basically applying 10 sine omega t type of signal, and if your peak inverse voltage of the diode is 5 volt, so then you cannot manage this kind of a process. So definitely this should be greater than or equals 10. So we can select a peak inverse voltage of 15 volt diode for this purpose. If your input is sine 10 sine omega t, so you have to select a kind of a diode which has a peak inverse voltage of at least 10 plus. So then referring this data sheet, you can select a kind of a rectifier diode for this purpose. If you are applying a voltage, peak voltage of 10 volt, so if it is like 5 volts 5 sine omega t, so then this 10 would be sufficient. So likewise you can basically pick a diode uh, accordingly. So next we'll move to so the next we'll move to this full wave rectification. So next we'll move to full wave rectification. So the very common method is this bridge rectifier bridge. Okay, so in that rectifier bridge, so we have this kind of a direction. Okay, so D1, D2, D3, D4. Okay, so if we consider this node, so this node is connected to the negative terminal of this diode 1 and positive terminal of the diode. So this is actually kind of a having alternative polarity. So similarly this node, so I have negative of D3 and positive of D2. So this is also kind of alternating. So if you just think about this node, so these both positive terminals of diodes are connecting here. So this is basically plus. So here this is basically minus. So these are kind of this node basically gets fixed DC, fixed value DC component, and you can just connect a resistor here. So these two basically have this alternating type of node, so then you can connect the external alternative source here. So A and B, So then C and D. Okay, so see what how this rectifier bridge works. So let's first consider this positive cycle. So we have this positive cycle. So then we apply voltage like this. So this is like this. Okay, so then so what about what happens to this D1, D2, D3 and D4? So if you connect this positive voltage to these two diodes D1 and D2, so we know that ideally if you connect a positive voltage to the negative terminal of the diode, ideally this should be reverse bias. So this should be forward bias because so we basically connect a positive voltage across it. So if we consider these two diodes D3 and D4, so we connect this negative polarity of this positive terminal of the D4 and negative terminal of the D3. So then ideally this should be forward bias and this should be reverse bias. So then what happens? So if this is reverse bias, so then you don't have this bias. Okay, so let's assume these are ideal set of diodes. So then these two during this positive cycle D2 and D3 become forward bias. Okay, so if those are ideal diodes, so there won't be any drop across these two, so you can basically replace these with open circuit, short circuit elements. So you can replace these two with short circuit elements. So then this positive polarity appear here and negative polarity appear here. So then ideally current, so there may be a current flow through this. So then the polarity of the resistor is like this. So the current is flowing into the positive terminal and leaving from the negative terminal. So we have this positive voltage here and a negative voltage, and there is a current flow through this one. So what is the voltage appear across this RL is basically VRL is basically equals to VI. Okay. So then if you draw this input, so during this positive cycle D2 and D3 on, and the output is actually equals to Vi. Then we move to the negative cycle. So what happens? What happens if we consider the negative cycle? So during this negative cycle, we have basically this kind of a voltage appear across this. So then if we consider this diode arrangement, so we have this kind of a diode arrangement. So then this voltage is something like that. So then this terminal would be positive and this terminal would be negative. So with this applied voltage, so this is basically off or reverse bias, because here positive terminal of the diode is connecting to a negative potential. Similarly, this get reverse bias and these two might be getting forward bias, because this positive terminal of this diode is connecting to positive potential. Here the negative terminal of the diode 1 is connecting to negative potential. So ideally these two diodes D2 and D3 get reverse and D1 and D4 get forward bias. So during this block, T1 and T4 basically on or forward bias. So then these are reverse bias. So these are forward bias. Okay, so then this is the positive polarity of the input. So then the current would be simply flowing like this. So again, this becomes plus and this becomes minus. So the voltage across this is still VI. So VI is a kind of a negative cycle, but the problem is, so across this resistor, so the applied voltage or the induced voltage is exactly same as the previous. So the direction of the current is exactly same as the previous, and the induced voltage also exactly same as the previous. So then it means whether you apply a negative cycle across its input, the induced voltage across the resistor RL, it is very similar to the previous cycle. So then your input should be ideally like this. So whether you basically apply this kind of a negative cycle, your induced voltage across this RL is pretty much same as in the previous, with the direction and the magnitude. So the in both cases, see, so the current flow to this direction. So then this terminal is act as a positive terminal of the resistor, and this would be negative. Similarly, once you move into the negative cycle also, the current flow doesn't change. The direction of the current flow remains as it is, and the induced voltage also definitely would be then synchronized or aligned with the previous pattern. So then you basically turning this negative cycle to positive. So this is called full wave rectification. So in the previous case with the single diode, we have this kind of output. So negative cycle is basically clipped and simply suppressed to zero. But with this 4 diode arrangement, this bridge arrangement, you can rectify the negative cycle as well. We can treat to the negative cycle as well. So during this negative cycle, the other pair, I mean like D1 and D4 diode pair gets forward bias and make it conductive, and the direction of the current flow through the load resistor RL remains as it is throughout these positive and negative cycles. So it basically entered from D node and leaving to the C node. So then all the time the direction of the current flow through the resistor RL is same, whether we are basically applying a positive or negative sign voltages. So the induced voltage across the load resistor would be similar to the previous cycle, so there won't be any polarity difference, so both are in same polarities, because during this positive and negative cycles the current flow through the resistor would be pretty much same in magnitude and direction. So then you will ultimately ended up with this kind of a pattern. So if it is a half wave rectified, you have this one and clip this one, and again you have this one and clip, right? So this is half wave, and this red color one is full wave. Okay, so this is the simple difference between this half wave and full wave rectification. And we can again use another kind of a method to do this full wave rectification. So it's through a center tap transformer. So it means we know that if it is, so if it is a transformer, we have primary winding and a secondary winding. So this is primary and this is secondary. So let's assume it's like 1 to 1 turn ratio. So then if you apply a kind of a Vm sine omega t type of waveform, if you apply Vm sine omega t type of a waveform, if the turn ratio is 1 to 1, definitely here also you can see a kind of induced voltage of Vm sine omega t. If it is 1 to n, so you have n times Vm sine omega t type of waveform. So if you have a transformer, very basic transformer, and if you apply a signal Vm sine omega 2 to the primary winding, if the turn ratio is 1 to n, it means like if you have 1 turn in the primary, so then definitely n turn should be in the secondary. So then the induced voltage across the transformer terminals in the secondary winding would be n times sine Vm sine omega t. Okay, so this is very basic. So if you tap at the center, if you tapped at the center, tapped at the center, so then the voltage appear across these two terminals A and B is simply divided into equal halves. So it means if your second winding is something like that and tapped at the center, so if the total voltage induced across this one is V out, so this becomes V out over 2 and this becomes V out over 2. So then the entire voltage across these two terminals, two endpoints of the coil is V out, and if you just take these two terminals, so you can basically have the half of the total secondary winding voltage. Okay, so the rest of the half is basically appear across the other part of the winding. So if you tap the coil at the center point, so we can basically split the entire voltage into equal blocks. So then for example, if you have a kind of a, so let's assume this is your Vm. So you basically have a voltage of Vm at the secondary. So then this, it means like the total voltage across these two terminals is Vm. If you tap this at the center of this coil, so then basically you have Vm over 2 here and another Vm over 2 here. Okay, so normal transformer has two endpoints, two nodes, in the primary. So those are the two endpoints of the coil. So if it is a center tap transformer, we have three terminals. So two are from the ends of the coil and one terminal come from the middle of the coil. So it's the center tap, the tap terminal at the center of the secondary coil. So then, so if we are referring the slides there, so we have this kind of arrangement. So we have kind of a coil, and here also we have coil. So it says that this is 1:2 ratio. So it means if you have V here, you have 2 times input induced at the secondary. So let's assume here we basically apply Vm sine omega t. So then you basically can get 2 times Vm sine omega t at the secondary. So then if you tapped at the center, basically this voltage would be half of it, Vm sine omega t, and this is again half of it, Vm sine omega t. So then if you connect these diodes like this, so what happens? So during this positive cycle, so we have a similar pattern induced in the second. But if this is Vm, this would be 2 times Vm. So this is actually Vm sine omega t, this entire voltage is 2m. So then we have Vm sine omega t like this and like this. So half of the secondary voltages appear across these two blocks. Okay. So then if we consider this network 1, so we have input voltage and a single diode. So D1, this is D1, this is D2. So then it's something like that. So we have this kind of a voltage. So then if you apply Kirchhoff voltage law, you can easily recognize that. So this diode 1 gets forward bias because the applied voltage across the diode is greater than or equal to 0. So then this first half D1 forward bias. What about this D2? So if you just apply the Kirchhoff voltage, so you can identify that the actual voltage appear across the 2 is minus of Vm sine omega t, so which is less than 0 basically. So then D2 basically would be reverse bias during this positive cycle. Okay, so then D1 is forward bias and you can see this kind of a current flow through this one. So then this flow is from this direction. So this is induced as plus and this is induced as minus, and if these diodes are ideal, then this input voltage simply appear across the resistor. So then during this positive cycle, so we have similar voltage across the load. So once we go to the negative cycle, so then the input is something like that. Here you have minus, plus, minus, plus. So then by looking at this circuit, you can easily recognize that D1 should be reverse bias due to this negative voltage. So then D2 is definitely forward bias due to the positive voltage applied across its terminal. So then this is on and this is off, then the current flow is something like that. So during this negative cycle also, so we have a similar current flow through the resistor and the direction also as in the previous. So then if we replace the diode with this short circuit element by assuming it's ideal, so the voltage applied across the resistor during this negative cycle is equals to the input voltage Vm sin omega t. It's basically. So then this would be something like that. Because here, whether you feed it positive and negative voltage across this transformer due to the direction of the current flow through the resistor, we can claim that the direction of the induced voltage also similar to the positive cycle. So then whether we have positives and negatives in the input side, once you rectified it, you will basically get a kind of a positive cycles in the output waveform. Okay, so this is the basics of rectifier circuits. So full wave and half wave rectification. Full wave basically we can achieve through a center tap transformer plus two rectifier diodes, or else you can have a normal transformer with four set of diodes, so diode bridge, to get the full wave rectification. So both are possible, and also you can purchase this rectifier bridge as a compound unit, a single unit from the electro market. So then it basically have four terminals. Two terminals you can directly connect to this AC source, and the rest of the two terminals, so it basically specify the plus and minus, so you can connect the load across this plus and minus, and so it's something like that. So if you go to the market and purchase a rectifier, that we have four also marked like this. So you can connect this one and this one to the source, and this is to the load. So this is the rectifier block. So I believe like you can get a kind of insight idea about this. And so next we will move to the another type of diode, which is should call Zener diode in next session. Thank you.